To coordinate flight, a fruit fly processes visual, spatial, and mechanical data in milliseconds to drive complex muscle groups. Its biological neural network executes this high-dimensional, whole-body movement with a mechanical efficiency that artificial systems cannot match. When engineers design artificial agents for embodied sensory motor control, they typically rely on multi-layer perceptrons, or MLPs. An MLP is a standard artificial neural network architecture where data flows in one direction through dense, uniform layers of nodes. These generic artificial architectures lack structural inductive biases. An inductive bias is a set of assumptions built into a model's initial design that helps it prioritize certain mathematical solutions over others. A recent computational approach discards the handcrafted MLT entirely, replacing it with a complete synaptic resolution connectome. A connectome is a comprehensive physical map of every neural connection within an organism's brain. This introduces a specific engineering problem, taking a static anatomical map of over 100,000 synapses and mathematically transforming it into a dynamic, functional algorithm capable of continuous robotic control. Solving this requires linking mechanistic whole-brain modeling directly to the reinforcement learning frameworks necessary to stabilize a physical machine in simulated space. This force-directed graph illustrates the architecture of the fly connectomic graph model, or FlyGM, built directly from the whole-brain connectome of an adult Drosophila. FlyGM imports the exact biological neural architecture directly without task-specific optimization. The foundational mathematical premise relies on the static synaptic weight matrix acting as a fixed, recurrent state transition operator. In practical terms, the physical wiring of the brain dictates exactly how information can flow through the artificial network. This diagram illustrates the sensory motor loop connecting the FlyGM architecture to the fly body, a biomechanical model in the MuJoCo physics engine. Controlling it requires continuous management of 59 independent actuators responsible for leg joints, surface adhesion, and body motion. To achieve this, the policy is trained via a two-stage pipeline. It begins with imitation learning, where the model trains on expert trajectories, followed by proximal policy optimization, or PPO. PPO is a reinforcement learning algorithm that fine-tunes the model's behavior based on environmental rewards. The resulting system establishes a direct computational pipeline from a static anatomical dataset to a physics-based simulated robotic agent. The primary translation problem lies in converting static binary connections between neurons into a dynamic, weighted flow of information. The researchers achieved this by assigning functional polarity to the connections, utilizing established cell type annotations and neurotransmitter classifications from the biological dataset. Excitatory neurotransmitters, acetylcholine, glutamate, aspartate, histamine, encourage the receiving neuron to fire. Inhibitory neurotransmitters, GABA, glycine, suppress it, creating competing inputs. To resolve this, they apply a signed weight equation. The final mathematical weight is the net polarized synaptic count, total excitatory synapses minus total inhibitory. This weighting scheme ensures the message-passing operation strictly respects the sign-preserving or sign-reversing nature of actual biological signal propagation. To account for unknown cell-specific computational properties not captured in the connectome data, each neuron also receives a trainable intrinsic descriptor. This acts as a localized gate to modulate the incoming synaptic drive. The network topology and the routing paths are strictly fixed by the biology, while the node-level gating parameters allow the network to adapt to the constraints of the simulated environment. This force-directed graph maps the tripartite partitioning of the connectome. To execute embodied control, the raw graph must be divided to handle the distinct phases of the sensory motor loop. The afferent partition consists of the specific subset of neurons biologically assigned to receive external sensory inputs. In the simulation, this observation input is a 1,253-dimensional vector containing continuous data on proprioception, mechanosensation, and binocular vision. The intrinsic partition contains the interneurons. These are responsible for building internal representations and mediating signals deep within the network structure. Finally, the efferent partition represents the motor neurons, responsible for translating those internal signals into physical outputs to the body model. In a full forward computation step, observations inject into the afferent nodes, aggregate through the intrinsic connectome operator, and decode from the efferent states into 59 continuous motor actions. Imposing this strict tripartite division forces the artificial agent to process high-dimensional physics data along biologically grounded, highly compartmentalized pathways. These sequence snapshots capture the results of the primary terrestrial task, initiating and maintaining a straight-line walk at a target velocity of 3 centimeters per second. The model executes the kinematics smoothly, maintaining a consistent body trajectory over hundreds of milliseconds without drift or collapse. These graphs track the joint angles and actuator activations enabling stability, isolating the temporal profiles of the coxa joints. An emergent grouping appears. The left front and rear legs synchronize with the right middle leg, forming an antiphase group against the opposite legs. This creates the classical alternating tripod gait observed in actual insects. Crucially, this specific stepping pattern was never explicitly programmed or manually designed into the controller. The precise topology of the biological neural network natively encodes the mechanical solution for hexapedal static stability. This raises a critical control question. Is FlyGM's success a direct result of its specific biological wiring, or is it simply a byproduct of having the massive parameter count of a 100,000-node graph? To test this, researchers measured FlyGM against 3 baselines: a standard MLP, an Erdos-Rainey random graph, and a degree-preserving rewired graph. An Erdos-Rainey graph is a mathematically generated network where edges are connected entirely at random, providing a baseline for unstructured complexity. This chart tracks total training loss as a proxy for sample efficiency. The biological connectome, shown in red, converges faster than unstructured baselines. These subsequent charts plot mean-squared error to evaluate trajectory tracking. Across all training steps, FlyGM maintains consistently lower error bounds. Furthermore, the structural advantages of the biological connectome compound heavily as task complexity increases. This sequence illustrates the high-yaw turning task, where the model executes a leftward turn at 10 radians per second. To achieve this, the stride lengths must modulate asymmetrically across the body. When subjected to this task, the non-biological baselines fail. While rewired graphs can maintain basic positional tracking, they suffer catastrophic angle errors and lose orientation stability during high-speed maneuvers. The completely random Erdos-Rainey graphs collapse entirely under the requirements of complex orientation control. A brain's wiring diagram is an optimized, evolved structural prior. Embedding it into reinforcement learning bypasses task-specific tuning, proving static anatomy serves directly as a highly efficient algorithm for embodied control.